Hello there, welcome to section 1.5, Solution Sets of Linear Systems. Solution sets are very important, you may find, in linear algebra, and these solution sets will appear in several different contexts. And in this particular section, we are going to be dealing with vector notation to give us explicit and geometric descriptions of these solution sets. So as always, we're going to start off with some terminology. And that is dealing with homogeneous linear systems. So the term homogeneous comes from a linear equation that is written in the form of AX equals 0, where A is some matrix and 0 is the 0 vector. So it could be however many zeros. A homogeneous system always has a solution of x equals 0. And that's called the trivial solution. And what we are interested in finding is the non-trivial solution. So this piece here is important. A non-trivial solution will exist if and only if the solution set has at least one free variable. And we will talk more about that free variable here shortly. So because we have that trivial solution and that 0 vector, all these solution sets must pass through the origin. So we are just going to jump right in into an example. And so we want to determine if the following homogeneous system, and I know it's homogeneous because it's all equal to 0, if it has a non-trivial solution, and then describe that solution set. So basically, we are going to make a matrix of the coefficients and then put the zeros in. So it will be the augmented matrix. And then we are basically going to row reduce until we get it to echelon form. So let's just jump in and see what happens. So setting this up, we have the following. Now, I have found that if you have one incorrect entry, whether it is a negative sign or a number, anything, you will go crazy. So check, double check, and be cautious. Okay, so what I want to do here is I want these to be 0. So what I'm going to do is add row 1 to row 2, and that will become the new row 2. And then in the same work, I'm going to do -2 times row 1 plus row 3, and that will become the new row 3. So when all is said and done, we get the following matrix. And moving along, now what I want, let's see, I want this to be 0 because we have a couple pivots here, and everything above and below, we want that to be 0. So what I'm going to do is I'm going to multiply row 2 by 3 and add that to row 3. And I get the following. Okay, so these are our pivots. We will eventually want to make these 1. But here we will notice that we don't have a pivot, and so this will be our free variable, and that's what we want. So remember, this represents x1, x2, x3, so x3 is going to be free. So since x3 is a free variable, we can conclude that this homogeneous system does have non-trivial solutions. And there will be one for each choice of this free variable. So if I want to describe this solution set, I guess let's answer the question, because the question says determine if the following has a non-trivial solution. So we will say, since x3 is a free variable, this has a non-trivial solution, or has, let's say, has non-trivial solutions. And as I said before, it will be one for each, one for each choice of x3. Okay, now if I want to describe this solution set, what I want to do is I want to continue to row reduce into reduced row echelon form. Okay, and I'm going to do that on the next slide just so I have some space. Okay, so I'm just going to copy this down and go from there. So just rewriting that and hopefully not making any errors along the way. Okay, what I want to do first is I want these to be 1 because they are pivots. So I'm going to take 1/3 times row 1, that will become my new row 1, and I'm also going to take 1/3 times row 2 to get my new row 2. So when I do that, I have 1, 5/3, -4/3, and 0. 0, 1, 0, 0, and then all zeros in the last row. Okay, moving along. If I want this to be in reduced row echelon form, I need this to be 0. So in order to accomplish that, I'm going to take -3/5 times row 2 plus row 1 to get the new row 1. So I'll have 1, 0, -4/3, 0, 0, 1, 0, 0, and then all zeros. Okay, now this is where things get interesting. This here is in reduced row echelon form. So what I'm going to do is I'm going to rewrite this as a system of equations. So I want you to remember that this row represents x1, x2, x3, x4. Or I guess that's what it's equal to. Okay, so when I rewrite this, I'm going to have x1 plus 0x2 minus 4/3 x3 is equal to 0 for this row. For this row, I just have x2 is equal to 0. And then here, nothing's happening, so 0 equals 0. Okay, so all I did was rewrite this using these as the coefficients of our equations to get this. All right, so this is basically my system of equations. Okay. All right. So what I want to do now is I want to solve for the basic variables. And my basic variables are wherever the pivots occurred, and that's x1 and x2. So if I solve this for x1, I get x1 equals, I simply add 4/3 x3 to the other side to get this. If I solve this for x2, well, that's done for me. And then x3 is free. So I have x1, x2, and x3. So now what I want to do is write this as a general solution. So as a vector, the general solution of ax equals 0 is, all right, so x is equal to x1, x2, x3. And we are just going to replace each of these with what we have written here. Instead of using x1, we know that x1 is 4/3 x3. Instead of writing x2, we know that x2 is 0. And if x3 is free, I'm going to leave that as x3. Okay, well now here, if I look at this, really the only thing that I have are multiples of x3. So I can rewrite this by taking out that GCF, essentially, of x3. And if I take x3 out of this, I'm left with 4/3. If I take x3 out of this, I'm still left with 0. And if I take x3 out of this, I'm left with 1. So this is referred to as my general solution. Okay, here is our next example, and what we want to do is we want to describe and compare these the solution sets of these two equations. And you may notice that these two equations are the exact same, except this one is equal to 0 and this one is equal to -2. So what we're going to do is we're going to solve this a similar way to how we solved number 1, but we're going to skip all the reduced row echelon part. So first I'm going to start with the second equation, and I'm going to solve it for the basic variable, which is x1. It's where the pivot is. So if I take this and I solve that for x1, I have x1 equals -2 minus 9x squared plus 4x cubed. Now this is the first part. So you may remember from the previous example, once we got here, we wanted to write a general solution. So this is the general solution with x2 and x3 being our free variables. So in vector form, the solution is the following. So I have x1, x2, x3. So instead of x1, I'm going to replace it with all of this. Now x2 and x3 are free, so I'm going to write x2 and x3 because those are free. So then what I'm going to do is I'm going to basically take out our GCFs and that sort of thing. Now, if I rewrite this, I will find the following, that I only have this constant here. So when I write my matrix of constants, I just have -2, 0, 0, because I don't have any constants for x2 and x3. As far as x1, you'll see that I don't have any x1s. So you can write this, but it's just like adding 0, so a lot of times we don't do that. Okay, but then next we have x2. So notice that we have an x2 here and here. So if I factor out my x2, I would have a -9, 1, and nothing for x3. Then for x3, I have an x3 here and here. So I would have 4, 0, 1. Great. Okay, so we're just going to let this sit here for a moment. And what we're going to do next is we are going to do the same thing, but for the other equation. Okay, so now in our other equation, if I solve this for x1, I will have x1 equals 0 minus 9x squared plus 4x cubed. Okay, so this is the general solution. With x2 and x3 being free. And these are free because I'm going to get a different solution depending on what I choose for x1, or I'm sorry, for x2 and x3. So those are free. So in vector form, the solution is the following: x1, x2, x3. So instead of x1, we are going to replace it with this. And then x2 and x3 are free, so I'm going to leave those as is. Now, in this case here, I don't have any constants like I did here. So I'm going to go on to x1. I don't have any x1s, just like I did right here. But it's trivial to just write that, so I'm not even going to bother because I'm a lazy American. So I'm going to next go to x2. x2 would be -9, 1, and 0. It's simply the coefficients of x2 in each row. Then for x3, I find the coefficients of x3 in each row. 4, there isn't one, and 1. Okay, now I want you to compare this to what we have here. Notice that these are the exact same thing, and let's just ignore this, right? So these are the same thing except this. And what we can do is draw some conclusions, and those conclusions I'm going to draw on the next page. So we can say the solution set of the homogeneous equation, so that's the first one, or that's the first equation, but the work I did second. So the solution set is of the homogeneous equation is the plane through the origin in R3, spanned by U and V. Because I can represent that, so I can represent, sorry, I wish it was here. So I had this. I can write this as x2 times some vector plus x3 times some vector. Okay, so it's spanned by vector u and v. Okay, so that's the solution set for the homogeneous equation. Now, the solution set of the non-homogeneous equation is parallel to this plane stated above and passes through the point P is equal to -2, 0, 0. And all that is the difference, which was that constant matrix. Okay, so they are the same thing, but the non-homogeneous equation is parallel to this plane, and it passes through this point. Now, this all leads to parametric vector form. So that equation that I was telling you about over there is called a parametric vector equation of a plane. So from that first example, we had a free variable, so that's what we're multiplying by. And then what we do is basically replace that free variable, and then we now have parametric vector equation. So sometimes we'll want parametric vector form, it just kind of depends. Solutions to that non-homogeneous system is basically what we talked about before, where P is that vector of constants basically, and V is the solution to the homogeneous system that corresponds to it. So this is probably like mind-blowing, and you're probably thinking, what in the world is she talking about? So let's look at another example, and it might kind of help. Okay, so here, this is to describe all solutions of this, AX equals B, where A is that matrix and B is that matrix. Now, the key here is not doing the whole row reduction thing, and it's really being able to give the general solution as a vector, okay? So, yes, row reduction is important, but by now you should be able to row reduce, and if you can't, then you need to reach out to me immediately. So I'm going to kind of skip some steps here and get to the heart of this section. So if I set up my matrix without making any errors, of course, I have this, okay? So I'm going to use row operations to produce this matrix. So this is me waving my hands and getting to this matrix. Okay. All right. So here, once we get our matrix to reduced row echelon form, then, so it has to be in reduced row echelon form, then write it as that system of equations. So x1, x2, x3. Okay, so when I write this, this is x1 minus 4/3 x3 is equal to -1. Here, x2 is equal to 2. And then in my last row, I'll just say 0 equals 0. Okay. Now, what I want to do is solve this and identify my free variables. So I want to solve this for x1, solve this for x2, and notice that I have a free variable of x3. So when I write this, I'm going to say x1 is equal to -1. Let's write it like this. I'm going to say 4/3 x3 minus 1. x2 remains the same, it's 2, and then I'm going to say x3 is free. Okay, so from here, I'm going to say, as a vector, the general solution of ax equals b has the form of the following. X is equal to, so x1, x2, x3, and I'm just going to replace each of these. x1 is really this, so 4/3 x3 minus 1. x2 is really 2, and x3 is free, so I'm going to leave it as x3. Okay. Now, when we write this, typically we will write the constants first. So identifying all the constants, we'll have -1, 2, and 0. Okay. Well, then we're going to add multiples of x1. Well, I don't have anything for x1 in row 1, 2, or 3. I also don't have anything for x2, but I do have x3. So I'm going to take out all my coefficients of x3. In the first row, it's 4/3. In the second row, I don't have any x3s, so that coefficient is 0. And then in the third row, I have x3, so that coefficient is 1. So I can think of this as this being my point P, because those are my constants, and then this being my vector, which is multiplied by x3. Okay, so notice the similarity to example 1 here. Okay, so if you want to pause and go back and look at example 1, you can. But I'm going to just draw some conclusions of this on the next slide. Okay, so the equation can be written as vector x is equal to vector p plus x3 times v, or writing as a parametric equation, so t as a general parameter. So I'm basically going to replace this with t. where t is in the reals. So this describes the solution set of AX equals B in parametric form. So the only difference from example 1, so if you went back and referred to example 1, the only difference is that we are adding on this P. So the solutions of this are obtained by adding the vector P to the solutions of this. And this is, vector P is just one of the many solutions possible. Some students find it helpful to look at a little picture of this. If you're visual, you can take a look at this or figure 6 in your text. It's up to you. But really, this concludes the section. This here talks about the different steps. So when you are looking for the parametric vector form, first you're going to set up your matrix and break it down into reduced row echelon form. Then you'll want to write your system of equations to identify the basic variables and the free variables. Then you'll write your vector x and then decompose it into a set of linear combination vectors. Okay, and any of the free variables, those will become the parameters. That concludes the section.